introduce our speaker. So we're shifting from general relativity to particle physics and computer simulations. Our speaker is Dr. Wahid Bhimji from the University of Edinburgh. He's a senior research physicist there, and he has been involved personally in the discovery of the Higgs Boson on the computer simulation side of things. This talk was supposed to be a joint talk again between one physicist and one philosopher, Michele Massimi, also from Edinburgh. Michele couldn't be here unfortunately today, but Wahid tells me he has a casual interest in philosophy, which I suspect is a little more than a casual interest in philosophy, and so he will be taking over also Michele's half of the talk. Wahid Bhimji, computer simulations and experiments.
Okay, thank you very much. Thank you. And thanks for inviting me here. So as suggested, instead of this being an experiment in bringing together a physicist and philosopher, it's now a simulation of a philosopher by a physicist. So I am an experimental particle physicist. I worked on the discovery of the Higgs Boson. I've worked on this paper with Michele, and it's basically trying to bring together so it's more of epistemology than perhaps some of the discussions that followed previously. It's about how we can know about the world through experiments and whether we can know about the world through simulations. So, key question is, are simulations we're not difficult to pronounce it. It's more difficult than epistemological. And also the word keeps underlining it as not being a real word. But anyway, are they on a par with ordinary experiments? And as this abstract here suggests, this has been part of an important literature. And actually, there's comments on this way beyond philosophy. There's a lot of people who casually say that simulations are a whole new way of knowing about the world around us. But the literature we're referring to here is, of course, the philosophical one. And as I've highlighted here, simulations seem to lack a distinctive feature of traditional experiments, namely the ability to causally interact with the target system. So it's this claim in particular that we'll explore a bit more from a philosophical standpoint, and then focus on the case of the simulation and discovery of the Higgs boson, which is something I know about, so quiz me more on that than on the philosophy, please. Well, I've blanked the conclusion here, but actually if you read the abstract in your printout, you can probably see what the conclusion is. Okay, so to explore more about claims about the epistemology of computer simulations, there's a claim made we call the causal interaction claim, and abbreviated sometimes as CIC in the say. That says that computer simulations lack a distinctive feature of traditional experiments, the ability to interact with the target system. So it's immediately appealing why this is the case. So it's saying that in order to do an experiment, I actually have to interact with what I'm trying to measure, and therefore by doing that, I learn something about it. And if I just generate a simulation that comes from a model, naively say, well, what I'll get out is what I put in, and I put a model in, and all I can learn from the target system about from the simulation is what I put in the simulation. So I can't gain any new knowledge about the physical world through simulation, is the claim. And that's kind of a paraphrasing of it. But from that, and so this you can get from other ways, is basically saying that perhaps because of this causal interaction failure, the simulation does not does not represent the target system in the same way as an experiment would. Okay, so this is something Geary picks up in the paper here. And then there's other claims that perhaps because of this causal interaction, experiments allow us to make inferences back to the target system that you couldn't make in a robust way with the simulation. Okay, so that's various claims, but they since these depend on this one, or at least can follow from this one, it's mostly the first one that we focus on. Okay, so the general overview of what I'm presenting is to clarify this claim. Then to describe, and I'll describe in some detail because I know about high energy physics and how we use simulation. And particularly this is in the context of the Higgs boson discovery. And in particular in two aspects of that come really in the final stage when you're actually uncovering a new particle from this. One is in determining the background, which is absolutely critical to knowing that a new particle is being seen. And we'll see it's as critical as it is seeing the new particle, essentially. And then interpreting it in terms of as being a Higgs boson. Their simulation again enters into the process. And so we'll focus on those two claims. And then, of course, we'll relate what we've seen about what happens in high energy physics to the causal interaction code. Okay, so first getting clear about the causal interaction code. Okay, so as I kind of indicated, a lot of this causal interaction can be thought of as measuring. So here's a little animation of the Foucault's pendulum, which is in the Arts and Métiers Museum in Paris, which is an excellent museum. And the reason I put pendulum here is because Geary, in his paper, talks about the pendulum and talks about the fact that various models are used to refine the motion of the pendulum when facing it with the real world. All those extra modelling, all those additions aren't the causally interacting part. What's important if you've got an experiment that's based on a pendulum is the pendulum itself, the fact that it can interact with the target system. Okay, so in order to try and explain this a bit better, we broke down the causal interaction into three kinds, which are 3 degrees of causal interaction. These aren't necessarily an exhaustive list of all the ways that one could causally interact, and they're not necessarily exclusive, but it's just to try and break down the different ways that causal interaction can be understood. So one is by direct causal interaction, whereby you do something like calibrate by direct comparison with the observed data, so you calibrate your experiment. Not only does this refine and tune the physical quantity to match the observed data, but in doing so, it tests the reliability of the instrument producing the observed data in the light of background knowledge we may have about the data, what the data should look like. And then the other two, and actually I'll use examples for these as we go through, so probably we don't need to go into detail on what they are here. The second is the quasi-direct causal interaction, where the actual causal interaction is going on in the world, but you design an experiment so that you're capable of tracking this. And the third is a far more indirect, where you actually interact with a background system in order to try and understand that, and in doing so you can infer a new quantity in the world. Okay, so then to give some examples. Okay, so these are examples of actual experiments that no one would dispute are experiments, and no one would dispute that you learn something about the world through doing them. So if we take the direct causal interaction, where I talked about things like calibration, then one can imagine the Balmer series, where this is just a brief description of what the experiment is. You have a discharge tube and then a grating, and you see a series of lines, which amazingly haven't come out very well on the projector, even though they're very pure colour lines. And I think this was referred to before in the previous talk as well. I mean, it's a manifestation of quantum mechanics, but of course these lines were described before quantum mechanics existed. But you can see the energy levels of hydrogen as rather beautiful coloured lines. And I think actually here is a connection between colour and experimental physics here, because it's the kind of sublime experience of colour that comes out during the experiment. That's how I felt when I did this as an undergraduate. But here, anyway, this is often used, knowing these frequencies very precisely is often used to calibrate instruments. Okay, so to take the second case, quasi-direct causal interaction. So as I said, this is where maybe two quantities in the physical world interact with each other, and you set up an experiment to track how this observes, how this behaves. So an example here is perhaps the Fitzhugh-Foucault experiments. So these are where you have a light and you have a spinning mirror, and you have another mirror very far away, and so the light can travel a long way and come back again and then back to your thing. And depending on the speed at which your mirror is rotating, you can make quite a precise measurement of the speed of light. and the other one, I can't remember which is Fitzhugh and which is Foucault. But anyway, one is to use a toothed wheel where the spinning of the wheel lets through the light in different directions. So here you're measuring one, you're tracking one thing using something else. Okay, so these are experiments, and these are causally interacting in different ones. And then the third way is indirect causal interaction, where, as I said, you measure a background very carefully, and that allows you to learn something about the world. And here's an example that's a little bit closer to particle physics, a little bit something I know, and this is Anderson's discovery of the positron in something we also mentioned earlier, the Wilson cloud chamber, where this is the first positron ever seen or something. And by understanding the cloud chamber very well, by understanding what electrons would do in this cloud chamber, which is basically to bend the other way because there's a magnetic field here and the positively charged positron bends one way and the electron would bend the other way, and what a proton would do in here, which is not bending in this way, not as much. Basically, this is exactly the same curve as you have in an electron, but in the opposite direction. Anderson could infer the existence of the positron. Okay. So that's kind of explored the causal interaction claim and where experiments clearly meet its criteria, that criteria. Okay, so now let's talk about simulation and the case of the Higgs boson. Right. Okay, so briefly, just to give some background, I'll give some background on the physics behind the Higgs. Particle physics tries to explain the world in terms of particles. So underlying us, there are atoms, of which there are nucleus, such as the proton. And inside protons, we now think of things such as quarks as being fundamental. There's up and down quarks that are in a proton, but there's also all these different types of quarks that we've since discovered in high energy particle physics collisions. We've then built up a picture of the particles in the world, which are both formed of matter particles like quarks and leptons. But we also think now of the forces, such as electromagnetism described earlier, as also described by particles, which these are called bosons. And so this picture of particles and the interactions between them has been an extraordinarily successful theory, in that it basically describes all experiments we can do on matter, in some cases to part per million precision. So it's really survived every test we can do of it. But it did have one missing piece, which was that there was no explanation of mass, and there was a mechanism for that that really had been relied on in the whole validity of the Standard Model, but never tested experimentally until recently. Well, it's certainly been tested, but never demonstrated experimentally until we discovered the Higgs boson. And now I can put this as a starting slide. Now I've got a Nobel Prize for it. It definitely exists, the Higgs boson. So we can put it on that slide, and it now completes this picture. So we have a complete picture of particle physics. Of course, it doesn't explain dark matter, which we know must exist from astronomical base. So we actually know most of the universe isn't explained by this, but everything we see around us is explained by everything we see and touch around us is. So that's doing quite well. Okay, so this is a plot that proves the existence of the Higgs boson, and I will actually come back to describing this in more detail later, so you don't have to understand it. But for this point, it's just the bump means there is a Higgs. So the bump is a Higgs. Okay, so instead I'll go on to just say how we look for the Higgs, and basically we have a huge collider that you may have read about. It's a big 27-kilometer ring underground at the French Swiss border, where we smash together protons that we accelerate to higher energies than have ever existed on Earth. We smash them together at various points around the ring, including inside detectors that enable us to see what's produced when these particles collide. So when these particles collide, lots more particles produced, and we detect them in experiments like the Atlas detector, which is what I work on, and it's a large thing. These are little people by comparison. So it's a huge detector, and I won't go into what all these terms mean, but basically it's comprised of several other subdetectors that each are sensitive to particular types of particle and can measure their momentum and energy. Okay, so here's what a collision looks like when you collide together these protons, and this is actually a real collision in the detector that's actually a Higgs candidate. So we can't actually say that this is a Higgs, and I'll come to that in describing it other, and there's probably philosophical implications about that, but I don't want to stray into that territory for now. But we can certainly say that this is what a Higgs would look like if it happened in our detector, and this is one that we saw. And so these lines here represent that the Higgs decayed to form muons, and we know they're muons because we see them in this part of the detector where we wouldn't have otherwise, well, no other particles could have got out that far and been detected. But one point to make here is that there's a lot of stuff going on that we're not particularly interested in. And this plot makes that point as well. So every time there's a collision, there's lots of things happening in the LHC, or in our detector specifically. So we need to understand this in quite some detail. And in particular, another point to make is that actually only around 1 in a billion, in the case of the Higgs, 1 in a billion of the things we actually produce in our high energy collisions are things like the Higgs boson that we're interested in. So the main thing that we need to do as physicists is a lot of filtering of this data to select the things that we're interested in. So there's a huge amount of computational power that goes into that. And so this is the plot of this. This is just to show that we have computers all around the world and they're all doing computing. This is a kind of publicity plot of that going on. And this shows that 100,000 computers connected across the world, and we have a lot of data as well, 100 petabytes of data. But the green in this plot here, so this is different types of work going on in these computers. The green in this plot is not the filtering of actual data that we saw at the LHC, but the actual simulating of other simulated data. And a lot of this storage is also simulated data. So we actually have to put a huge amount of effort into simulating things, which is basically taking the models of the Higgs boson, or things that we hope to see, and seeing what they would actually look like in our detector, so that we can compare with what we see in the detector and unravel what physics was actually there. Okay. So that leads on to simulation. And so now I'll just try and describe simulation as it is in high energy physics. So basically, simulation in high energy physics involves kind of 3 distinct processes, or at least they're not necessarily distinct when they run, but they can be described as distinct. And so I'll go through these in a little bit of detail, which hopefully won't be too boring, but at least it gives you a clearer idea of what simulation means to us. Okay, so the first stage is event generation. So this is actually simulating the underlying theoretical physics. So theoretical particle physicists and even experimentalists actually love Feynman diagrams, which I use there. So I find them an easier way of visualizing what's going on, but probably many people who are not physicists do not. But basically, this represents the incoming proton collision in terms of quarks and antiquarks, and then some interaction and then various things happening. But actually, these so these Feynman diagrams allow theoretical particle physicists to make predictions, but these predictions can be quite complicated because, for example, this shows a quark traveling along and various gluons radiating off it. And you can in fact keep having gluons and keep having quarks produced, and keep having gluons, keep having quarks produced, and each of that is part of a calculation that goes on. So they often have to use computer models just to do these calculations. They often have to use simplifications to do that. And moreover, they also have to compare with actual experiments, previous experiments or whatever, to refine the computing model they use. So already we're seeing in this process that simulation is not something that is just a model. It in fact already has experimental input into the model itself. So there's already this kind of crossover between what's simulation and what's experiment. Okay, but basically the output of these models is a probability distribution for different types of particles and their energy and momentum. And then we use something called Monte Carlo methods to be able to draw a sample for these. And the idea is to have what is at the end a list of events that correspond to the kind of things that you get in collisions at the Large Hadron Collider. So if we had 1,000 collisions, we might want to generate 1,000 simulated events that have the right statistical distribution. So that's the output of this. Okay, that's then passed into the next stage, which is called detector simulation. And here we have basically a very precise description of the experiment, of Atlas experiment itself. So that's including all the electronics, all the material, all the empty space, all the pieces of iron, all the wires, the support structures, and everything that's in there, and how that would react to these kind of particles being produced. Now again, experimental measurements can go into this. So if you don't know how, if you don't have a model for how an electron will interact with a piece of iron, for example, you could do an experiment where you fire pieces of electrons, electrons of particular energy, into blocks of iron and measure their response. And that's what you do. That's what you often do here to refine this simulation. And so we basically have something where we can build up, and these plots just kind of show building up a complete geometry of the experiment and how it reacts to these particles. And the key idea here is that the output you end up here with is a kind of detector signals. So these are actually what the experiment, these are actually comparable with what the experiment itself is producing. And then I mentioned something briefly here that's perhaps just adding a little bit of confusion, but I think it's interesting because we also add additional hits. So the point is that not only is the physics process that's simulated going on, not only has the hits occurred, but there might be cases where the beam of protons hits a bit of gas or something, or hits the edge of the beam pipe or something and produces some background as well. And you have to mix this into the event. Now, on Atlas, we do this with additional simulation, but on an experiment I worked before, this was actually done with an experimental measurement. So making a measurement where there was only one beam in the machine instead of colliding beams, for example, and then adding that in. And the reason I mention that is again, it's another case where experiment is kind of merged with simulation, experimental measurements merged with simulation to produce something more useful, if you like. But simulation no longer has a distinct nature in that. Okay, and then finally, we pass this into something called event reconstruction. So this is basically, as I said earlier, this is the same software as used in events from the real detector. So in an example I give here, these are various detector layers. And so you want to measure the passage of tracks, and you say you want to know where they came from. But all you have is certain hits on your detector in certain points, because you haven't covered the whole specs, you've only got detectors in these places. So you can extrapolate back from these points to what is actually the true one, in this case, but you can also draw different lines through these points. So what we do when we're reconstructing particles on the real detector is to draw lines through all these points, make a kind of statistical distribution, and go, oh, this is the most likely origin for all of those points. Okay. Now, in the case of the simulation, you think, well, why would you do this? Because you could just say, well, where did I make these particles from in the first place? But the point is, you want to apply the same thing to the simulation that you applied to the original, to the actual experiment. So that if you only have a 50% chance of getting the real events in your real experiment, you only want a 50% chance of getting the events in your simulation, and you want to know that probability so that you can, as I said, be equally imperfect, and you can work out how likely you were to see the Higgs boson or whatever actually in the real detector. Okay. Okay, so now I've now described simulation in high-energy physics, which is in general true in all high-energy physics experiments. Now I'm going to come to a specific use and how simulation is used in the discovery of the Higgs boson. Okay, so simulation is used a lot, as I said here. I mean, I kind of vaguely mentioned, I guess, that simulation is even used in the construction of the experiment, in designing future experiments, in calibrating each part of the detector, and so forth. So I'm only going to take two illustrative examples, really right from the end of the physics analysis process. So one is background determination, where simulated data is used to determine the nature and amount of other particles that would have occurred to the collision, so that you can actually see that there's something new here. So you can only know that there's something new when you've actually simulated or worked out what what the standard model particles, what the particles that you already understand look like. And then in interpretation, where you've seen a novel particle, but how do you know that it's a Higgs boson? Well, the standard way is to simulate a Higgs boson and use that to interpret what you've seen. Okay, so first I'll take background determination. Okay, so to first explain one thing, I did mention that the Higgs decays to particles, and that's what we observe. So we actually observe the particles that the Higgs decays into. But here I'll be talking about two specific decays of the Higgs. One is to 2 photons, so two photons coming off of Higgs. Again, the final diagrams are not particularly important, it's just a way that I have picturing it. And the other is to 2 Z bosons that in turn decay to leptons each. So these are muons or electrons typically. So the general way that the analysis works is to first of all do a lot of filtering so that you know that you saw 2 photons or 4 leptons, and then to measure the energy and momentum of these particles, add them up and form an invariant mass, and then that would be the mass of the Higgs boson if it existed. So you end up building a plot like this, and this is another kind of publicity animation which shows time going on and data being gathered here. And basically this kind of plot, it shows this invariant mass that I talked about on this axis and a frequency count on here. It's a histogram. And so every time you see something of around 150, you put a little entry in here and the picture fills up as we go along. And so that's just a publicity plot, but it's probably easier. I mean, so I'll let it play to the end, but it's probably easier to see in a fixed histogram. So as I mentioned, the black points, or maybe I didn't mention, the black points are the actual data. These are actually what you've seen in the experiment. As I point out here, it's after you've selected various things to concentrate on what you're interested in. The red and purple, so ignore the light blue for the moment, the red and purple are the background. So those are what you expect to see from things that aren't the Higgs. And basically, the fact that the black data points are much bigger than the background of what you expect to see proves that there's something new. That's the whole essence of discovering the Higgs boson, essentially, or discovering a new particle, I should say. So what we actually do is to calculate the probability of this background accounting for this discrepancy. And you may be able to see a small hatched region here that is the error on the background determination, as I'll explain in detail how we determine the background a bit. And we've now calculated that the probability, well, in this plot, the probability of that background actually being responsible for that bomb is less than 1, I believe. Okay, sorry. All right. So these backgrounds in this plot come from simulation, following the process that I described initially. That process is done, these backgrounds are generated for the production of 2 Z bosons, for the production of Z plus jets, or top quarks. Okay? So those are the underlying event generations, then it's put through the full detector simulation, then you make this plot like this. And the reconstruction. So the observation depends on this. So I'll stress again that without doing this process, you wouldn't be able to observe the Higgs boson. But you actually need to not only know what this plot looks like in terms of the shape, but also how high it is in this plot. Now you could do that again with theory and with even the event generator process that you use, and that is what's done for the red plot. But for the purple plot, so I call it Z plus jets here, for the purple plot, there's in fact a different approach taken, which is data-driven. So what we do there is in fact to look at another variable, such as this, and this is the mass of the 2 highest momentum leptons instead of all 4. Here, we don't expect to see any Higgs in this plot. So we can directly take the data, and we can directly take the simulation that we've produced, and we can scale one to the other. Right, so that's done with a fit, and that gives you a scale factor, and then you apply that scale factor to the other plot to kind of normalise the background in that plot. Okay, so that process that I just described is important to the kind of points we want to make here, which is that the comparison between simulation and experiment can be thought of as a kind of validation of the whole simulation process by making it encounter real data. It can also be used to calibrate the simulation, and that's often the case that one goes back to the original model, which it's not a precise model of what's going on. So there's various parameters you can tune to tune those parameters and to make another simulation which is used to compare. So one example is, for example, the fraction of quarks producing a proton-proton collision, which isn't known precisely in the model. Okay. However, in this case, you didn't do that. You didn't go back and make another simulation. All you did was to scale the simulation you had. Right? So I think this is a kind of creates a kind of hybrid, if you like, in that the plot that you made does not directly correspond to any theoretical model. It corresponds to, it only exists as a kind of hybrid of simulation and experiment. It's no longer just a theory. Okay. And then I like to consider the other case, which is the Higgs decay to 2 photons. Right. Now, so this is the same kind of plot, but made with the invariant mass of the 2 gammas, the 2 photons. And so again, it's a frequency count, but you see there's lots more entries in here. And so actually there are error bars on these plot points, but they're extremely small, so you basically can't see them. Then in this case, they also make a plot here where they subtract the background from the bump, and then you can see a more clearer bar, if you like, and clearer errors on that. But the point here is that actually, because this shape is quite uniform, all you do to determine the background here is fit this shape. So you basically extrapolate from these areas where you do not expect to see a Higgs underneath the bulb and say this is background here, this dotted line, and then they subtract that here. So while this is checked with simulation, because you obviously want to check that the processes that you understand do not also bump under here, because that would kind of defeat the purpose, the actual extraction of the background, and therefore the observation of the particle in this case, doesn't use simulation at all. Okay. Okay, so I can take a little summary. Simulation is a key part of the LHC experiments. This experimental detection of the Higgs depended on the background determination as much as the observed data points, really. So you couldn't, really the background process is part of learning something new about the world. So that means that simulation is an integral part of the experimental discovery of the Higgs boson. However, this background can be taken from experimental measurements or simulation. So in 4 leptons, we saw that we not only had simulated data, but that this was treated in a kind of interchangeable way with the experimental measurements. It was modified by it, all with the goal of getting the error down on the measurement. It wasn't treated as something special or unique or in some way a different kind of knowledge that one gleaned from experiment rather than simulation. And in 2 photons, we didn't use simulation at all. We need them in order to extract them. And as I said, it can also be a hybrid model. So to make a philosophical point, I think it's impossible to draw a distinction between simulations and ordinary experiments. Okay, but now we have a second example, which actually I should have got to a bit. So now we've determined a new particle, but we need to establish that it's a Higgs, because otherwise Peter doesn't get his Nobel Prize and Edinburgh doesn't get all its extra Higgs sensors and all the extra cash. So again, we simulate with the same 3-stage process a model of the standard model Higgs. So this is saying use the physics of the Higgs that was described by the standard model and make a like one here. And then you can compare it with the dots and see how good it is. So you make a statistical fit, basically. So you can do this by eye and say, oh, I've done a pretty good job, actually, because this looks like this. But what you actually want to do is make a statistical fit of the size of this compared to how much you would expect in the standard model. But also, you want to generate this with different masses. So you actually put different masses into the model and see how well it fits this peak. And that gives you a measurement of the mass as well. And so here I make a brief point that in order to find the mass, we as I mentioned, it's a computationally difficult process, all this, so you only do it with discrete mass points, but yet you want to come up with a mass that's 125.5 or whatever. So you also want to extrapolate with values in between those, and cause morphing for some reason. But again, I want to make a quick point that this could be done without simulation. You could, in principle, just measure the height of this peak and its position and mass, and say that was the mass. But you would probably have some error because points shift around here. You could use some experimental correction. So for example, this is a Z boson. So you could say, how much has this shifted? This is something I know the mass of. How much has it shifted? And then you could correct your mass because of that. So there's no reason, in principle, why you have to use simulation to get this result, but we do so because we can. So again, simulation is a key component of the analysis. You wouldn't get a Nobel Prize without it, but you can use it interchangeably with experimental or theoretical methods. So I'll just finish up by saying what we can learn from the Higgs case. Right, so to go back to our initial readings of causal interaction, the first one was about direct causal interaction, where one interacts with the target system in order to calibrate the experiment, let's say. Okay, so I mean, probably it was a good choice of words to use calibrated in the two cases. As I mentioned before, we often use calibration to when we're talking about simulation. We calibrate our simulation by encountering it, by bringing it to meet real data. But then also, I mentioned this specific case where we actually directly compare the data with our model and use that to correct the amounts that we put into the final histogram to extract the Higgs boson. So Michaela here says, this is an analogous way to which the reliability of the spectrometer is assessed by comparing experimental data about the hydrogen spectrum within the Nobel series. So here we can see a relationship between what's done in an experiment and what's done in simulation. Okay, so if we take our second reading about quasi-direct causal interaction, so this is where you're trying to track something in the physical world by using your experiment to do so. So here a good example is the Higgs mass. So as I said, one is used to can measure the Higgs mass by tracking its behaviour via using different simulated samples with different mass values and different coupling rates. So here you have a kind of quasi-direct way of tracking what the physical underlying quantity, the mass, was. And this is a plot that probably doesn't really help clarify anything, but it's another plot from our observations on Atlas that shows the mass determined from the Higgs to 2 photon and the mass determined to the Higgs to 4 lepton. And I mainly put it here to show that these are actually different values that you get from the two, and the black is where we combine them. So that's one of the intriguing puzzles on the physics side, is whether these are actually different. I mean, they're not really statistically different, but maybe with increased data we can resolve this, whether this is a real difference or not. And then the third reading was indirect causal interaction, where one's measuring a background and then inferring something about the real world for this. And obviously, I think one can tell from the language I've been using throughout that this is very strongly what we do with simulations in particle physics and in the Higgs discovery in particular. That most of the experimental work goes towards designing ways of determining and controlling the background against which the hypothesis. A hypothesized particle can be reliably inferred. So this is the plot I showed before, where basically understanding this background is really actually key to the whole discovery. Okay, so I'm ready to move to conclusions. Basically, the thesis that there is an epistemological difference or priority of ordinary experiments doesn't really hold in these readings of causal interactions. So in all of these cases, all these different ways you can read causal interactions, which is not necessarily exhaustive, but the important thing is that there are different ways you can read it, and that those different ways are also the case with simulation. So, does this mean that the detection of the Higgs boson and its properties necessarily depend on the new simulations? As I said here, no, that isn't the case in that 4 leptons. The reason I draw this out in particular is there is some literature that says that that overstresses it the other way, perhaps, that the computer simulations are absolutely essential. And that's not the case, because some rely more on others. They need not, so the whole detection need not be entirely entangled. But on the other hand, to add a kind of counterbalance to that, this does not imply that they're not important and key part of the experimental practice. And in fact, it just goes to underline this point that it's an integral part of experimental methods. With that, I'll conclude.
Brilliant. Thank you very much for that. That was very helpful. And I think we've got plenty of time for discussion.
Yeah.
Oh, thank you very much. I very much enjoyed that. In a way, I wonder whether you were protesting almost too much. In a sense, there is a dialectic between, as it were, elaborating theories and formulating more and more precisely the observation one would expect to support those theories, and then doing the experiments. And I think I'm totally persuaded by what you said, which is, it seems to me that this is just an extension, as it were, of the theoretical predictive phase of any kind of science project, followed by obviously the testing phase and so on. So I'm completely persuaded by your argument. There's nothing epistemologically or epistemically different about computer simulations. It's just a refinement of the hypothesis phase of this iterative process of going from hypotheses to testing and back to hypotheses. Or have I, in a sense, simplified what you said?
Yeah, well, actually, I grappled a bit during this of whether I thought that was true, that it was just an extension of the model. So it's just like a way of taking a theoretical model and turning it into something you could compare with the experiment, which we clearly see in some of the examples is what's going on. Or whether it was actually an extension of the experiment because of the way it's used interchangeably with data-driven results. So instead of using a simulation, one uses some experimental measurement. So then it seems actually an extension or a tool that's related to the experimental side of things. So I think in truth it's not actually either, but it's still not a whole new philosophy of science, if you like, which is what some people think.
I wonder if I might just volunteer a sort of sociological observation, which is from the condensed matter side of things. I mean, in a sense, the difficulty here is partly the difficulty that sometimes goes under the name of emergence. I have some set of fundamental laws, but I'm about to do an experiment on very particular physical conditions, and in conditions where many hundreds of particles may be created, and it's not immediately obvious what those laws tell me will happen. And so it is, I think to echo the point just made, that feels like an extension of the theory, in the sense that it's asking, if I wish to apply this theory to this experiment, what will it tell me? And as we well know from condensed matter, where we've known the microscopic laws for 90 years now, but are still having difficulty using them to predict what will happen in particular experimental situations, it can take a lot of theoretical work to get from the microscopic equations to what one expects. The sociological observation, however, is the following. It is that there tends to have been a division, at least in condensed matter, between the kinds of computational elaboration of the theory done by theorists and the kinds of computational elaboration of the theory done by experimentalists under the heading of data analysis.
Right.
And so, whether or not it's methodologically separate, there are in fact two communities of people who are more or less separate from each other doing these two kinds of thing. I wonder if that might cause us to think more than we should that the simulations are an extension of experiment just because they become attached to experimental projects.
Right, yeah, because experimentalists maybe have the sort of skills of it, yeah. So, I mean, well, so in particle physics, the event generation part is very firmly done by theorists, in fact. So even though it's a kind of, it's not done by the string theorists who are headed in the clouds, it's done by the more practical theorists maybe, but still it's done by them, not by experimentalists, so it's different unity. Whereas the rest of the process is done by us, and we have to bolt in those often Fortran codes into the other stuff. But I mean, in terms of your example, I mean, there's also a kind of, so there's a case where you might use it if it's too tedious to work out on pen and paper, or it's even impractical to do that, so you use a simulation to do that. But then there's also a case where maybe it's impractical to design the experiment, even in condensed matter, so you design a simulation to simulate that situation. And then you might, so often with climate models, for example, where the actual experiment would be the size of the Earth. You can't in practice do it, so you build a climate model, and then you actually kind of experiment with that. So it is really very much like an experimental situation. So I should probably have mentioned that the concern that some people raise is that this is important because people are reading too much into, or drawing too much from their models. So this is an experimental model, if you like, that they're doing experiments with that, and then they're making conclusions about the real world, which they shouldn't be. But then, actually, a counter-example is that, as you said, in some cases, that's maybe true of all experiments, is that you have a simplified experiment in the lab, and then you draw an inference about the real world from that. So I don't think it's distinct in that. But anyway, yeah. So, sorry, I verged away from your point initially, but I do think it's both an elaboration of theory and also an experiment in itself.
Thanks. So someone's view that there's a limit on where we can go in particle physics because the energies have to get higher and higher, and you'd have to have an accelerator that was bigger than we could build and that kind of thing. Does simulation offer some hope for kind of going to higher energies than we can practically do, or do you think it wouldn't be accepted unless you're also doing experiments?
Yeah, I did. Well, yeah. So that's in a real case where I don't think you could. So one thing it does allow you to do is to kind of consider what will happen at higher energies, which might influence what kind of experiments you build in the future. But I think this is kind of the key point that people who talk about the limits of simulation talk about, is like, how would you discover, say there was some exotic, dark matter thing that was only produced when we collided together things at 20 TeV, which is a bit higher than that. How could your simulation possibly tell you that? Because either you put it into the simulation, in which case you'll see it, or you won't. So that in that case, I think, you can't do quantum physics by simulations alone, essentially. But in other sciences, I believe they do essentially do that. They do push forward the boundary of the science, because it's like, let's say, a complex sort of system. So you can determine the emergent phenomena by simulating it without having to do the experiment. And those are actual real phenomena that you can do also.
So that's what you're on about the climate.
Yeah, so that's like the climate one. But I do sympathise a little bit with the people who are making the points about simulation, because whole papers are produced where they basically took a climate model and tweaked some of the parameters and said, this is what we saw. And the climate model doesn't actually predict the real increase of temperatures or whatever. So it's become kind of an esoteric field in itself. Got arms and legs of its own. So that you can see that concern. And there's also another concern which is related, which I didn't bring up, but maybe it would be the subject of future work with Michaela, which is about what people are now call big data, which is basically where you have so much data that you can learn something without actually having a hypothesis to test in the first place, that it kind of just emerges from the data. And they're calling this a new kind of science now. And so computer scientists are knocking around this term called the fourth paradigm, which is almost inviting philosophers to respond. So
it's actually an alternative to simulation, that's kind of something else again.
Well, yeah, so this fourth paradigm is saying that like theory and experiment are the other two paradigms. This is obviously a wrong use of the word paradigm. And then the third one is simulation. And then the fourth one is taking it a step further to just use data. And so you can, so there, you have a little bit more sympathy, and we haven't really thought out of views at all on this, but there you can imagine a situation where, say for example, Google is collecting all this data and putting all these trends about things, without hypothesis, it's determining conclusions about things and maybe building up a model of the world, and then potentially applying that. So, making predictions, if you like, all of which is done by a computer without human involvement at all. And then it does seem to be a kind of new kind of knowledge, because we don't even have the knowledge in the computation. So, yeah. So that's kind of where. So I think there is something generally in computational methods that this kind of black box and approach that's something that philosophers could respond to.
Thank you.
I'm full of admiration for the extraordinary amount of work that goes on in these experiments. From my experience, at least as much work goes into the simulation, building the computer model of the detector, as building the actual detector. It's a staggering amount of work. But there have been a few cases in the past of slight embarrassment. So very, very carefully simulated experiments have been done in one part of the world, and the error bars down to 1 or 2%, and then done somewhere else, and they're also down to 1 or 2%, but they're 10% different from one another. So there's always this danger of systematic errors creeping in here or there. With the LHC, we face a fundamental problem. There's only one machine.
Yes.
So does that give cause for concern? How's the link between the Atlas and CMS experiment? Are there any other concerns about systematic errors? And are there any surprises we might anticipate from LHC? It's one thing to find something that you're expecting to find, but are there any early hints of some other juicy things?
Nothing I can talk about.
Okay.
So that is part of the problem, and this is why the US wanted to build a superconducting supercollider that was shelved. The point, I guess, the thing is we do have independent experiments in the actual collisions that occur inside the CMS detector and inside the Atlas detector, which are both located at the LHC, are actual independent events. And then supposedly everything about the detector, all the people working on it, if you're an institution, you're not allowed to be a member of both, is supposed to make those kind of independent experiments, so they can cross-check each other, and they both see the Higgs, for example. So I think that's quite compelling, but on the other hand, these people share the same office building as CERN. So when the initial hints of the Higgs boson came out, particularly as there was very little, I would show that mass plot. Actually, the whole rest of the mass plot was being excluded before they discovered the Higgs in one place. So when there was the first hints, it did kind of seem like maybe this was sociology or something, or one group convincing another group to see it. But part of what convinced me is that was seen in 2011 data or whatever, and then the analysis was frozen. They kept the same selections and then applied them to 2012 data. So that's what's called blind analysis. So that's where you can't keep tweaking what you're looking for based on what you see. And then you still saw this startling, even more significant in both sets of data. So that's So I think we're doing the best we can without, no one wants to build another several £billion. And the thing is, you can also get indirect handles on things from different ways. So actually now looking back on it, it's obvious that the Higgs would be there because there's all kinds of indirect measurements where the most favoured value for the Higgs mass was exactly where it was found. So now it seems like everything is scale and then in terms of more exciting things, basically, I kind of hinted on that plot maybe, but we do see this mass difference that I don't think is significant and will go away, particularly as CMS don't see it either. But the other thing we see is that this is systematically, well, not systematically, but it's somewhat higher than what the standard model will predict. So 1 on this is what the standard model predicts, and we see something higher in this one. Right? So I think actually with more and more precise measurements, and with measuring things in other channels, we might find something. And then for me personally, we have to work on the Higgs because we're everywhere. But for me, the step up in energy, which we'll have, offers us the best chance we'll have for a while to see something genuinely new. So one can hope that we will,
I have a question actually. So certainly the LHC is the biggest machine in the world, and there's a lot of very smart people working on it, so they're quite certain what they say. But I'm wondering about experimental certainty. because the mass plot that you showed has 2 peaks. And that one.
This one here?
Yes.
Yeah.
Comparing that to the one with the 3 circles that you just showed, to what extent is it valid when there's only 2 peaks? I mean, 4, 5, 6 peaks would be great. 1 peak, would that be dismissed? But 2 peaks is, how can you say with certainty that you have this sort of distribution when the rest of the frequency sampling, the sampling frequency and the resolution of mass is so limited?
Right. I mean, so on this plot, you have this peak, which is the Higgs. So which other peak are you referring to?
Yes, those 2. No, the blue ones.
The blue? Yeah. Oh yeah, so these 2 data points, basically saying, these histograms, yeah. Well, how can you be certain? Well, because, I mean, you can calculate, which I didn't put on this slide, you can calculate the probability of this going up to this, you see. And you can say, I mean, it's really because you say you understand this very well, but I mean, it fits all of this. It fits the other distributions that I showed 1 plot of the 2, fits that. It fits this peak nicely. And so, all in all, from this kind of systematic checks and from other checks, you come up with the error on here as being this hatched line. And then if you believe that, then you believe the peak. And to be honest, I believe that peak quite distinctly. And then also, yeah, so the other plot also showed it in 2 channels. So you see a peak here, but then you also see it in the gamma-gamma one, which is yeah, so you also see it here, which is a whole different process. And here you have also several bins in. So, yeah, so I think you can do a statistical treatment, which involves Bayesian statistics and all kinds of things, but eventually I think you can, once you have enough data, you can be reassured that you have it.
Would we still be certain if there's only just 1 point instead of 2?
Well, yeah, it depends on the errors and everything, but yeah, I think you're right. I mean, in a case like, for example, the top part discovery in Fermilab, when they first discovered that, or when they were going to claim discovery, when they only had 1 event, so they just had 1 thing, so there was a lot of desire to publish that because they thought they understood everything, the background as well, but there's discussion within the community when it comes down to those kind of low statistics, whether it's really meaningful. And there have been warning cases like pentaquarks, which is the most famous one, where there was some new types of particles discovered, which are called pentaquarks, which was then confirmed by several other experiments and turned out to be false. So we definitely are very, very cautious in what we produce. So I think we can have some confidence in this. And eventually everything becomes clear. Like, so the other peak here, this is the Z boson. So, at one point that was a discovery, and because in the fullness of time, it's background knowledge.
Yuki, any more questions or comments? No? In that case, let's thank our speaker again.